There is a bit of do behind me. But the blogger at Pharyngula, the scourge of creationists, the scourge of religionists, the professor of biology at University of Minnesota Morris, Professor P.Z. Myers.
Okay. All right, so what I want to talk about today is I'm going to talk about the evidence for evolution from development. And to give you a little context here, I was very excited a couple of weeks ago because the creationists at Uncommon Descent posted a set of questions for me. Some of you may have heard about this. A list of 10 plus 1 questions that I am supposed to answer in the talk today. And I looked at those questions and I said, man, there is a flaming moron in Scotland who wrote these questions. So I thought, okay, what I'm going to do is I'm going to give you sort of the background to understand why these are bad questions and why they completely missed the boat. Now, I'm going to first show you, let's see if this works. Anyway, what I've got up here is I've got some of the questions, and it's just to get you started thinking about these questions. And then I'm going to ignore the questions for a while, and I'll just give you the story I'm trying to tell you. But, you know, the questions are things like, doesn't Darwinism predict a pattern wherein the earliest stages are most similar and the later stages are the most different? There's a whole bunch of, like I said, I'm not giving you all the questions here, but they've all got this fundamental error in their premises. Because the answer to that first question is no. So we're done. We've basically answered all the questions. But I'll explain to you why that's total nonsense and why the rest of it is just gibberish. And we will work our way through these crooked slides. Uh-oh. Oh, okay. So what I did, I've just given my talk this title because this actually turns out to be the center of the premise that will answer the issue for you. Some of you may know I have this little blog called Pharyngula. And people are always wondering, why did you give it that strange name that nobody can spell and most people can't pronounce? And it's because this is the stage of development I'm most interested in. The Pharyngula is a particular stage in development, which you will see in a moment is the focus of all of our interests. This is where the interesting developmental things that represent global interactions that set up the form of the animal occur. And so what I'm going to do is give you a little bit of the history of this, of ontogeny and phylogeny, and I'm going to tell you how it's all been tangled up, and we'll talk about von Baer and other good people, all the way up to modern day Evo Devo. And I'll have a few awkward detours in here to talk about Haeckel, who is kind of... Haeckel doesn't get enough credit. He was really a smart guy, and he did some good stuff. His big problem was that he was wrong. If any of you are scientists, I'm going to warn you right now, the one thing you have to make sure you aren't, so that your name will last forever in a good way, is don't be wrong about anything. And sometimes that's hard to do. Okay, so a little bit of the premises here. This is a famous quote, all science is either physics or stamp collecting, from Ernest Rutherford. You guys may have heard of him over here somewhere. He's on the other side of the Atlantic from me anyway. But anyway, famous scientist. And when I read this quote, my first feeling is, man, Ernest Rutherford is full of shit because he doesn't know about biology. And the other is that he's actually right. That, in a sense, okay, that there is a kind of stamp collecting science where you just collect data, you just lump things together, and that's not very interesting. That you need more to your science than just a heap of data, a collection of facts in order to make sense of it. So, a few rules here. A catalog of facts is not an explanation. If I just gave you a litany of the molecules that are present in the developing Pharyngula, you wouldn't learn a thing. What you need to know is how these things work together. Theory affects our understanding of evidence. This is something we have to be aware of. Francis Bacon himself talked about this, that when you've got a theory, it actually colors how you interpret the data. This can be a bad thing if you've got a bad theory that's leading you in a wrong direction, but it can be a very good and powerful thing if your theory is on the right track. Because then what you'll find is that your theory leads you in productive directions. And there's one more down there near the bottom. Understanding the history of science is also essential. That one of the critical points to understanding science is being able to answer the question, how do you know that? That, again, you can't just give a litany of facts. What you want to know is what experiments were done to determine that. How can I trust your results? Can you explain to me how you came to that conclusion? If you can do that, then you're in pretty good shape. Now, what I want to do now is I'm going to talk about some of the facts. So first I'm going to just show you a couple of slides, and I'm going to lay out the bare bones facts, the facts that we have to explain. And the first one is this one. Okay, this is a pharyngula. A pharyngula, as I said, is a particular stage of development. In human beings, you hit the pharyngula stage about a month after fertilization. So this is early in the second month of pregnancy, is when the fetus is going through this particular period. And what's happening in this, well, let's see, I got a laser pointer. What's happening in this stage is there's a couple of features that are present. It's a little bit clipped here, but you can see. One is that if you look along the back, there's these little ridges here. Those are myotomes. So the body is segmented. So you got this segmented pattern that you see reflected in adults in the arrangement of vertebrae down your back. These are tetrapod embryos. So you also see these things developing here. These are limb buds. It's got a tail. There's a postanal tail right there. There's one right there. And, oh, it's over here. But anyway, yeah, there's one there too. You've also got this peculiar structure of the head. So this is the head of the animal. And what you have are these things here, which are called branchial arches. And colloquially, they're sometimes called gill slits. They're not gills. What they are a basket of little branchy processes coming down that contain a mix of tissues and can do all kinds of wonderful things, as we'll see. So basically, when you were a fetus, your face from about your eyes down was gone. And what you had instead were these things dangling down and fusing at the midline to form a kind of basket there. So that, like I said, those are branchial arches. These are the structures of the pharynx, the throat, and this is where we get the term pharyngula. The other thing about this image up here is I've got 3 pharyngulas up here. They are 3 different species. Can anybody tell me what they are? No. No way. None of those is. Yeah. What's that? No, there are no chickens up there. One is a human, yes. Which one? The left, somebody said. Okay, I'll tell you if you got it right in a moment. What other animals do you see up there? A what? No. Yes, there's a dolphin up there. Okay, what else? Snake. No, it turns out snake embryos look really different. I'll show you a snake later on. Now, the other one is a cat. You're familiar with these things called cats? So there's a cat, a human, and a snake up there. And we've had one guess so far that this is the human, and I'll tell you that that's wrong. This is the human over here. That's the cat, and this is the dolphin. You can't tell these things apart. You know, if you're a real expert at embryological anatomy, maybe you could. There'd be little features that you could recognize that would help you to tell them apart. But most tetrapods, you can't tell apart just by this morphology. Other things that will distort these is the presence of yolk sacs and stuff like that. But here I've picked 3 mammals, and the mammals don't have yolk sacs, so that doesn't distort them. And you can see, that's why I was laughing when somebody said a chicken. Chicken would be a big yolk right there. And no, there's no yolk. Okay, so this is a fact, that there is a stage of development. It's called the pharyngula stage. And at that stage, vertebrates resemble each other a great deal. Don't let anybody try and tell you that that's not true. It is. I have had many creationists argue with me and say that this is a total lie, and it's not. I can bring you into my lab. Yeah, just get in a plane, fly over to Minnesota in the United States, take a car about 3 hours west, come to my lab, and I will give you a tour. I have a whole set of slides, and I can show you all these different animals, and you'll say, how the heck do you tell those apart? And the way you tell them apart is a little label on the slide. Okay, here's another fact. I just told you that there are these cool things, these branchial arches. What do the branchial arches do? In a human being, hello, there we go, okay. Here's a little diagram illustrating, here's the pharyngula stage embryo. There are those branchial arches, and in this diagram they have nicely color-coded them for us. So each one is a different color. And what will happen as the organism proceeds from this point on is that those branchial arches get greatly modified. Like I said, in the embryo, you've got a face that's mostly missing. It's just got these dangling bars down there. And what they'll do is they'll expand and grow, and there'll be other tissues like neural crests that migrate down and fill in spaces. And it will build a face out of that will look like this. And you can see where these things end up. For instance, this first branchial arch is going to form the core of your jaw. The second one is going to form part of the hyoid cartilage and this thing called the styloid ligament, and it's going to form one of the bones of the ear. And the third one, another part of the hyoid, and then there's the thyroid cartilage, the thing, your Adam's apple is also formed from one of these arches. So we're going to have this gross remodeling of these pharyngeal arches to build a face out of it. Now that's really interesting. It's also kind of bizarre. Why is your face built this way? Why don't we just form a face, it's like clay. Let's just imagine it just molding into a face. But instead, all we tetrapods, all we vertebrates, go through this stage where we build this funny little basket, and then we take that basket and we flip things around and move things around and rebuild it until we have what looks like a face, which is very strange. So we have to explain this. We have to explain why all vertebrates look similar at the pharyngula stage and why they go through this peculiar stage where they have these strange structures that are remodeled. Okay, so let's talk about the history of the theories to explain this thing. So let's go way, way back. Oh man, I wish I could read that. Anyway, this is an old theory from C.G. Karras in 1835. In the early years of the 19th century, the center for most of the thinking about this was in Germany, a school of thought called the Naturphilosophen, who were busy speculating about this phenomenon because they were aware of it. They knew that this was going on. And they built models in their heads, which they didn't test very well in laboratory experiments, which is a major failing. And their first explanation was this one. It's called recapitulation. And it says, boy, now I wish I'd memorized it. The degree of development of a superior animal constantly recalls a determined form, don't break it, a determined form of an inferior organism. But between the two, there's no complete identity, but only a resemblance of a fundamental something or other or essence. Good enough. Okay. What is this saying? Well, what they're saying is this is not evolution. They didn't believe in evolution. This was over 20 years before Darwin published his book, remember. What they had in mind, the major concept they had was the great ladder of life. That you could categorize different organisms on a hierarchy. So you have a big ladder. Down at the bottom, there's jellyfish. At the top, there's human beings because we are the best. And in the middle, you have all these other intermediate forms, like monkeys up near the top, mice down near the middle. So you can take any organism, they thought, and you can place it on this ladder. That's why they can talk about things like superior animals and inferior organisms. Humans superior, jellyfish inferior. And this has nothing to do with evolution. This was actually a religious concept that they had, that in the mind of God there was a pattern. And that pattern was a ladder, a hierarchy with superior at the top and inferior at the bottom. And you just have to fit animals into this. And what recapitulation theory was saying is that when you develop, when the embryo is growing in the womb, what it is doing is climbing the ladder. So you start off as an inferior form, a little blob like a jellyfish, and the embryo then progresses up the ladder until it reaches a superior form, us, the final human form. And there was this whole elaborate theory to explain various things. So for instance, you may know that Down syndrome used to be called mongoloidism. And what they argued there was that was a person who'd climbed up the ladder and hadn't gotten quite to the top because, of course, it was white human beings that were at the very top. So they were at a slightly inferior grade of development. So it was a useful explanation for, they thought, for explaining a lot of phenomena in developmental biology. It's also totally wrong. Now, I got to mention this lovely man. Don't you love his beard? This is Carl Ernst von Baer. He's kind of a hero of mine. He was a contemporary of Karras. He was probably the greatest embryologist of the 19th century, and I would say actually the greatest embryologist of all time. Just this amazing intellect, brilliant guy. He made all kinds of discoveries. He's the guy who discovered the mammalian ovum, for instance. They didn't know until he found it whether there was actually an egg inside human beings that would develop into an embryo. And there was actually some speculation that maybe there wasn't. So he's the kind of guy who goes in there and finds this and figures it out. He was also cranky, irascible, elitist, superior, snobbish, really brutal in his criticisms of other scientists. Now, I'm not as brilliant as Carl Ernst von Baer, but I can at least emulate that part. So that's what I live for. Anyway, Carl Ernst von Baer looked at this problem. He said, no, you're wrong. You've got the wrong interpretation here. And first I'll mention that Carl Ernst von Baer, well, I'll mention a couple things first. Carl Ernst von Baer was not an evolutionary biologist. Again, he worked mostly before Darwin. After Darwin came out, he was his usual cranky, irascible self, and he criticized Darwin all to heck. Didn't believe that stuff at all. So this is not evolutionary theory that he's proposing. What he did is he came up with his own independent explanation for this phenomenon. And first I got to mention, he confirmed the facts. Remember I told you facts, right? That vertebrate embryos resemble each other at a particular time of development, and that those variations then diversify into the different forms of the face. This is a quote direct from Carl Ernst von Baer, where he's describing how he's going through his lab and he found a couple of vials that he'd forgotten to label, and there was some embryos in there, and he couldn't tell whether they were lizards or small birds or very young mammals. So I'm just saying this so I can tell you, yeah, Carl Ernst von Baer confirmed the fact. Now what he's going to do, though, is he's going to give the explanation for why this occurred. And he gave a very different explanation from this idea of climbing a ladder. And you are not going to be able to read these at all. These are Carl Ernst von Baer's rules, his laws that he thought described this process. And what he says there is, I'll just summarize it. Instead of climbing a ladder, what he said is that yes, there's a period in early development when they're very similar. But then the reason they're similar is that they are expressing the most general characters. So I mentioned that the things that were common to all those chordate embryos I showed you were things like the somites, the segmentation of the body, the presence of limbs in tetrapods, those branchial arches, those structures up there, the postanal tail that extends out back. Those are general characters that all animals have, all mammals, all tetrapods. So what he was saying is, no, all that's happening here is not the appearance of a primitive animal. This is an animal that just started forming. It's like, you know, again, if you were sculpting something, if you were sculpting a bust, what you would do is you would first make a little spherical thing, a little oval-shaped thing, right? A little egg-shaped structure. And it wouldn't be because human heads go through an egg phase. It's because that's the general overall structure. And so he's saying the same thing here, that what's going on in development is that animals first build a rough outline. All they do is say, okay, well, I'm going to make limbs here. I'm going to make 4 limbs. I'm going to make a tail. I'm going to make a head with facial structures. And it's a rough sketch. And the reason all these different animals resemble each other is because it is only a rough sketch. If we had an artist here who wanted to draw all your faces, what would he do? He'd draw a little oval first, right? Make little marks for where the lines and the nose will go. And no matter who among you he drew, the first few rough lines would be the same. It's when you start adding the details that it gets different. So what his explanation was, yeah, you start off in a very general form, and then what begins is each different organism differentiates in its own specific way. It builds its own specific form. So what you have is an early phase where everything looks the same, and then new things get added to make it more and more different from other species. Okay, all well and good so far. And of course, Carl Ernst von Baer presented this scathingly and just yelled at the Naturphilosofen and said, no, you're all wrong, this is the explanation. And of course, they ignored him. But nowadays, what you would say, if you talk to a developmental biologist and you ask them, why is it so? They will point to Carl Ernst von Baer's laws and say, this is the reason why. This is the explanation. So this is theory number 2 to explain this phenomenon. Okay, like I mentioned, von Baer is pre-Darwinian. Then this guy comes along, Charles Darwin. And in his book, this is something we developmental biologists brag about a lot. Darwin says, embryology is, to me, by far the strongest single class of facts in favor of a change of forms. Charles Darwin cited embryology as a really important piece of evidence for evolutionary theory. Now, there's a couple of reasons he did this. Okay, again, hard to read, but I'll just summarize once again. What Darwin recognized was that there are different ways to classify things, right? And that what you want to do if you want to talk about the relationship of different organisms is you want a robust classification. You want to use as many characters as you can. You want to look at fundamental features and how they relate to each other. And the early development of the embryo is a fundamental feature. So he's saying, here's another tool that you use to classify organisms and show their relationships. So for example, if you were looking at a couple of cars and you want to know whether they're by the same manufacturer, what would you do? Well, you might look at the engine, or you might look at the chassis. You might look at, identifying marks in there, see if it's true. You probably wouldn't look at whether they have an air freshener or fuzzy dice hanging from the mirror, right? That's a useless criterion for determining whether those are the same make of car, because they're late additions. You look at the primitive stuff, the stuff that's laid down when it's first manufactured. Same argument here. So he's saying, if you want to really establish the primitive relationships of different organisms, you have to look at embryos. Similar embryos suggest similar origin. Okay, so that's what this thing is. And he's just talking about this. He also, again, cut off here, he also mentioned that there are reservations about this. He's saying, don't just blithely accept it, because there are significant differences, especially in larval characters. So he's saying, yeah, you can look at those fundamental features and you can see key relationships, but sometimes you'll see differences. And you have to account for those differences. It's again like you look at the car and you dig down deep and you may find that a truck and an SUV have the very same chassis from the same manufacturer, but the truck has a bigger engine. The fact that it has a bigger engine does not rule out the relationship. So he's saying you have to do careful analysis. And I mention that because he's not blindly accepting just these superficial similarities. He's saying look deep, and looking at the embryos is how you look deep. Okay, then we're going to come to theory number 3. And it's cut off over there, but in parentheses it also says number 1, question mark. Because what happened is that there was a reinvigoration of recapitulation theory at this time. Because what happened is this guy, Ernst Haeckel, comes along. This is a quote from Darwin about Professor Haeckel. Ernst Haeckel comes along and he says, the old Naturphilosofen, I said they explained it as climbing a ladder, a hierarchy from primitive to superior. And Haeckel said, well, we also do this in evolution. We evolved from these distant primitive ancestors to our modern form. And he proposed that development was a process of repeating your evolutionary history. So he's saying, with a different rationale, that yeah, development is going from jellyfish to fish to frog to mouse to monkey to man. That's his argument. This actually found favor with Charles Darwin because Charles Darwin made a big mistake. Okay, his general theory of evolution was built without knowledge of a theory of inheritance. He didn't know how genes worked. And Charles Darwin at this time proposed a theory called pangenesis. And pangenesis said, well, basically, you've all heard this. You've all heard of Lamarck, right? Lamarckian inheritance. Charles Darwin, it should be called Darwinian inheritance because that's what Charles Darwin proposed, is the inheritance of acquired characters. That, for instance, as an individual developed, if an individual, for instance, works really hard, they're a blacksmith and they build up gigantic muscles, those gigantic muscles that he built up by use can be passed on to his progeny. Seriously, he really thought this. This was his whole argument. Knew nothing about Mendelian inheritance. So he proposed this, and which raised an interesting possibility. If you're a blacksmith, for instance, and you build big muscles, when do you do this? Do you do it when you're an embryo or when you're an adult? Obviously, when you're an adult. So that's a late addition. And that's being added to the embryo. So the idea was that every embryo is simply stacking on top of the previous developmental program new features that it acquired during its life. So that when you look at development, you are seeing a recapitulation of all of its history. Okay, Ernst Haeckel was the guy who came up with this idea. He coined this very well-known phrase, ontogeny recapitulates phylogeny, which is just a fancy way of saying that in development you go through your evolutionary history. Now Haeckel, as I mentioned, is an underappreciated fellow. He was kind of a heroic figure, actually. He was an adventurer, an explorer. He was prolific in his writing. He was apparently a marvelous speaker. He explored lots of different places. He did undersea exploration, all kinds of cool stuff. And he also invented lots of things, like that ontogeny recapitulates phylogeny phrase, but he also invented whole fields like ecology. Ecology came out of Ernst Haeckel's brain. So he was a smart guy. Now, like I said, he's going to make a big mistake, and here's his mistake. This is a famous diagram. This is Ernst Haeckel's recapitulation diagram, and what it shows is these are different species with the labels cut off down here, I'm sorry to say. Anyway, this is the Pharyngula stage here, and as Ernst Haeckel drew them, they're all very similar. I'll tell you right now, he tended to exaggerate the similarities. He simplified a bit, and you'll see why in a moment. This is an intermediate stage where they're becoming more different, and here farther on you can see more similarities. So like there's a chicken, there's a pig, this is a sheep, this is a dog, and again over here the cutoff is a human being. So you could organize these, and you can still say, well, they look very similar here. They become progressively different as they get older along that axis. Now, this diagram is frequently criticized, especially by creationists who object strongly to its inclusion in textbooks of biology, which is a little bit unfair. They claim that this was plagiarized, it was faked, and this is completely wrong. This diagram is an honest illustration of the developmental stages. What happened is a little mix-up in history. Ernst Haeckel took a shortcut, and in another diagram he cheated, and he reused a woodcut a couple of times and labeled them with different names. And he was caught at this, and he was severely denounced by his university for this behavior. And since what has happened is now everybody seems to think, oh, he faked all his data, and he didn't. He faked one drawing, and I will show it to you. This is Ernst Haeckel's famous fraud. Oh, there we go. This is it. This is one diagram from one of his books. And what it is it's supposed to illustrate the formation of the somites. And what you can see, as marked in this little box right here, if you look at these, there's this little quirk in the drawing where this somite is malformed. It's also malformed here and here, and this is something, I think this was a chicken, a turtle, and a mouse. And it's pretty obvious when you look at those little details. You got to admit it, Ernst Haeckel cheated. He fudged this. This is unforgivable. This is a very bad thing for a scientist to do, even if it is in this small, trivial little diagram. So he's been thoroughly cussed out for this. The diagram I showed you before, though, that one wasn't faked. There were no complaints about this. His contemporaries had no objection to those. They had the same data sitting in their labs. Now, this theory from Haeckel, ontogeny recapitulates phylogeny, though, it's wrong. There is that early stage where they're very similar. All the scientists have confirmed this. But what is not true is this business of recapitulation. They do not recapitulate. That what you find is from that one point at the Pharyngula stage where they all look very similar, they all start diverging from one another. So mammals follow one track, birds follow another track, reptiles follow another track, which is exactly what von Baer described. Okay, so we're saying right here, okay, Ernst Haeckel got it wrong. He cheated a little bit on some of his diagrams, but not the main ones. Recapitulation does not occur, so this ontogeny recapitulates phylogeny phrase is completely wrong. Don't use it. And the question is, we're still left with an explanation to make. We are thinking right now it's von Baer's explanation, theory number 2, as I showed you when we blew by it. How do we resolve further things? Well, the answer is, if you want to resolve further depth to the theory, if you want to check out whether the theory is actually right, what you do is you gather more data. This scientific empiricism stuff. Theory can only carry you so far. What you then need to do is you need to look at the organism and see if it can tell you more. What this is a photograph of a fruit fly embryo. This is the head of the developing head of the embryo. This is its body and its abdomen curling around here. So it's kind of constrained by an egg case. So it's actually a long worm-like thing that's just curled over on itself. And what you see here is that each of these different colors is a different molecular probe. So in this case, what we're staining for are these things called Hox genes. And each Hox gene has been coupled to a different fluorophore, a different chemical to make it a different color. And what you find when you do this is that there are these bands along the length of the animal. So what we found here is a molecular foundation that's present at the Pharyngula stage. If this were a vertebrate, this would be the Pharyngula stage. It's the phylotypic stage in flies, but it means the same thing. And among these molecules that are found there are these Hox genes. The Hox genes have got everybody very excited because what they seem to be is part of the formula defining the body plan. Only part, not the whole of it. I got to show you another diagram here. Okay, what this is to summarize these. Up here at the top is a fruit fly, and it's color-coded. So there's Hox1, which is up here, and then there's Hox2 back behind it, Hox3, 4, 5, 6, 7, etc. So we can see that these make those little bands. So each of these is localized to a particular place in the embryo's body. The cool discovery was, once they had identified these genes that affected these body parts, he asked, okay, where is it in the genome? Let's go look on a chromosome and see what it looks like. And here's a surprise. When they sequenced the chromosome, what they found is that all of these genes were clumped together in a big group. Unfortunately, in flies, it's broken into 2 groups, but most other organisms, it's one big group. And what they found then is here's a color-coded gene for this part. This is labial. This is another gene that's just behind there. There's another gene for back of the head there. There's some thoracic genes in there, abdominal genes, etc. The cool thing they discovered is that they were in the same order on the chromosome that their order of expression is in the body. What that means is 3' end of the DNA, there's this molecule being stored. That's expressed in the anterior part of the animal. posterior genes are expressed at the 5' end. So it's like this little map located in the genome, this linear map of positions along the body. Okay, this is cool. This is exciting stuff. We want to know how this is all regulated, how this generates the different forms of the body. But I'm going to talk about something slightly different, and that is what happened next. Is this work was done in flies, and when it was done in flies, they pulled out a bunch of these genes, and they had the sequence for the genes, and they could do things like say, okay, let's make a probe. Let's make a lovely little probe that sticks to this sequence of DNA, and that glows blue, or glows purple, or glows red. So we can throw it on the fly and see that part of the animal light up. In science, there is a policy that you should be open in your data. We're not always, but you try to be. And so the people who made these probes made them available to people. You could write to them, and they would send them to you in a little test tube. I actually did some of this with some other genes, not these particular genes, but other genes, where I wrote to this lab in Germany and said, hey, I'm working on this molecule. Can you send me your beautiful fly probe? Because I want to see if it works on fish. And here's where the cool stuff happens is it turns out that these same probes would work in lots of different animals. And we could apply these to, for instance, a mouse and ask, what do we have in the mouse? And that's what's illustrated in this part of the diagram. This, again, is a chromosome right here, 3' to 5' end. And when you looked, there was a homolog to the fly gene right there, another homolog to this gene, homolog to that gene. You found homologous genes ordered in the same way on the chromosome. Now this should be screaming out in your head, common descent at this point. All animals share these genes, and they're organized in similar ways, and they have similar functions in marking out different positions along the body. So when we look at these Hox genes and how they're expressed in a mouse, which is this diagram down here that's on the door. Anyway, the main point is you see the same thing. Anterior, posterior patterns of expression that very much resemble what you see in the fly. So we're saying, okay, here's a mechanism. Here's something that appears early in development. It's important in specifying the organization of the body plan, and it's shared between all these creatures. It's not shared just among mammals and vertebrates. It's also shared with arthropods, which is very exciting. Now, I said the other thing we do is we're out to collect more data, right? Another thing people did is they had to check and reconfirm Haeckel's observations. Remember those drawings? They're just drawings. And I told you he fudged them a bit. He simplified, he emphasized similarities. They're not that great. So some people have gone on, and here, for instance, is a collection of photographs of embryos at these stages. And what you see here is these are laid out exactly like Haeckel's diagrams, only we've got many more species here. So there's lamprey, dogfish, gar, salmon, lungfish, axolotls, a kind of salamander, another salamander, snakes, chickens, possums, and cats, bats, yes, and humans. Thank you. So we got this wide range of them. And what you find is that early on, you might be looking at those and you say, oh, you know, there's a lot of differences I see there, and you'd be exactly right. There are differences at the Pharyngula stage. They're not all exactly identical. But they're roughly similar. They all have the same structure. They all have branchial arches, myotomes, tails. In the cases of the tetrapods, these creatures from about here on up, they've got the limb buds. So we see these general similarities, but we also see differences. And most of the differences can be accounted for by distortions caused by yolk. Think of a chicken egg. It's gigantic, right? That's a huge pile of yolk that's hanging off the belly of the embryo. Whereas if you look at a human embryo, there's no yolk, so they're unaffected by that distorting structure. And I'll show you a picture in just a moment that illustrates that. You can also see that they rapidly diverge from one another. I mentioned snake earlier. I love that snake embryo. Look at there. In order to fit in the egg, what they do is they make this little corkscrew for the long body to fit within that structure. But again, it's in detail it's different. In general structure, it's the same because it is also made of somites It contains a tail that extends past the anus, all the features that we find in these other organisms. And of course, obviously, as they get further and further progression, you can see distinct differences. So none of you would find this creature, a bat, very cuddly, but you might find a baby pretty cute to look at. Okay, so what's going on here? Well, a couple things. All right. Yes, we're all over the place here. This is another diagram illustrating this general principle that what you see across the top on the ceiling there are the eggs. We're looking at the earliest stages. And what you find when you look at different organisms at the earliest stages is big differences. Again, you knew this, right? Chicken eggs. You eat these things for breakfast. You break them open. You look at them. They're huge. This gigantic yolk. And there's a little tiny embryo, if it's a fertilized egg, sitting on top of it. Whereas you look at other animals, no, they may have small amounts of yolk or variable amounts of yolk. As is shown in this down here, here's an illustration of a chicken egg. There's a giant ball of yolk, and there's the itty-bitty little embryo on top. If you look at a frog like this one, the yolk is more distributed. It's in the cells. It's not in a big mass like this. If you look at a fish, it's more like a chicken in that it's got this large yolk mass, but it's a smaller yolk mass than a chicken, obviously. If any of you have seen fish eggs, you know, much smaller than a chicken egg, but sometimes much tastier. And there over here is a mouse, and a mouse doesn't have any yolk at all, and so it's just got this sheet of cells for the embryo. And then, of course, what happens is they enter the pharyngula stage, and here's the pharyngula stage. As I mentioned, there are obvious differences, okay? This chick is distorted by a yolk that's been cut away. This is the fish. This is the animal I'm most familiar with working with. It's got this giant ball of yolk here. It's just kind of curled around that. And this animal, this mammal, lacks that yolk. But the same structure's there. Branchial arches, somites, tail, everything in general is the same, slightly different in detail. And then finally they go on to develop into adults that are radically different. So what is this diagram showing us? It's showing us that early in development, different organisms are very different. They then converge on a similar form at this pharyngula stage, and then they diverge into the adult to make the different kinds of adults. This has been illustrated with this little diagram. It's called the developmental hourglass. It's a very common kind of illustration of what's going on here. And all this is showing is that if you look at the egg, where the width of this hourglass represents animal diversity, the different forms that we find. So they have a great deal of diversity in eggs. It converges on this phylotypic stage, which is the narrow neck of the hourglass, where you have a smaller amount of variation. And one of the things developmental biologists are concerned with is to measure exactly how wide is this neck. Is it very narrow? Is it a little bit wide? We don't know. We're working on that. And then from this point on, they follow von Baer's rules, and they diverge into the adult, into the different forms of the adult. Okay, how do we explain this? Well, this little diagram over here explains it all, right? It's obvious now. You all understand. What this is a diagram. So we've got time. Time is going this way. So this is young. This is old down here. What this is, this hypothetical line right here, this is not something you can actually measure quantitatively, but you can sort of qualitatively detect it as you look at the embryo, is that early on, there's fairly little global interaction, but there's a peak. There's a peak of global interactions. And what does this mean? Well, those Hox genes, remember I told you they're turned on this pattern from front to back? They're specifying the order of things in the body. Basically, you've got this one little period where it's like when the surveyors are staking out the house before they build it. They just drive pegs into the ground and say, okay, this is the west wing, this is the master bedroom, this is the bathroom, and so forth. That's what's going on here, is that there's a pattern set down in the embryo that says, okay, this is the head end, this is where you're going to put your forelimbs together, here you're going to put the hind limbs, here's where you're going to put the tail. And that's assembled for all organisms at this roughly the same time, and it's depending on a whole bunch of interactions that extend the length of the animal. After this period, though, global interactions drop off, and now it's more local. What does that mean? Well, once you've staked it out and you say, okay, we're going to build a forelimb here, and we're going to build a hind limb here. My hind limb does not need to talk to my arm in order to carry out its developmental program. These things will develop autonomously at that point. So we can stop talking to each other. We're going to use rules of symmetry and general rules of growth to determine the relative size of these structures and to build out the various details. So what this argument is saying is that the reason you have a pharyngula stage is because of molecular interactions that have to work across the entire animal in order to make sure it doesn't make mistakes, like putting its legs on top of its head. And that animals are more free to diverge after that point, because once you've started the limb growing, it's going to follow its own program, doesn't need to talk to the rest anymore. So that's why you can have a conserved pharyngula stage and a divergent adult form. Okay, that's a general explanation. Now I want to talk about some of the creationist explanations, and I'm going to tell you that they're basically idiots and liars. And I have to single out this man who I consider the most contemptible, despicable, cruel, vicious, evil liar in the creationist movement today. Yes, he's a nasty, nasty person. This is Jonathan Wells, and part of it's personal because I'm a developmental biologist, as I've explained to you. He has had training as a developmental biologist, but apparently it didn't take because he doesn't understand anything about fucking developmental biology. And he's written a couple of books, Icons of Evolution, which creationists keep trotting out at me, and I love it when they do because it is the most pathetic piece of scholarship I have ever read. It's really poorly done. He's also written this one called The Politically Incorrect Guide to Darwinism and Intelligent Design, another really bad book, which has a number of points in there, and I just want to mention one. He says, intelligent design is based on scientific evidence, not religious belief, which is an egregious lie. There is no evidence for intelligent design. All it is a rationale for a creator. That's all they want out of this. And it's total nonsense. Now, what kinds of things do we know about him? This is right there at the bottom of the screen. Can we lift that just? This is an infamous quote from Jonathan Wells where he basically confesses that the only reason he has gone out to get an advanced degree in biology was so that he could discredit evolution and, as he calls it, Darwinism. So he's a Moonie. He's from the Unification Church, and I'm not specifically singling out the Unification Church because I think Christianity in general is a load of crap anyway. But he specifically went into this to battle Darwinism, that he came in there with a bias, and he obviously didn't learn anything. Now, here are the creationist claims that you will find commonly stated. They're in Wells' book. They were also in that set of questions I mentioned before. He says, evolution is built on a foundation of Haeckel's recapitulation. Who believes that? Anyone? No, I just told you that's bunk. Haeckel was wrong. We know he was wrong. We showed he was wrong. We found genes that show he was wrong. We know that the pattern didn't follow his described pattern. So you cannot claim that evolution is built on Haeckel's recapitulation. We discarded that theory in the late 1800s. Okay? Then they claim there's a conspiracy of silence among biologists to hide disconfirmation. I've often had creationists come up to me and say, oh, well, Haeckel lied about those embryos. They didn't really resemble each other. And you're lying to me when you say they're very similar. And I say, I'm going to grab you by the ear and drag you into the lab and sit you down my microscope, and you're going to look at these things, and you will learn, yes, they are very similar. And of course, when you talk to people like Jonathan Wells, they think the brave scientists of the Discovery Institute are the ones who are responsible for exposing the truth that we've been hiding. Not so. As I told you, Haeckel was shown to be wrong in the late 1800s, a little bit before the founding of the Discovery Institute. Creationists had nothing to do with developing the ideas, developing the molecular biology that explains development in our modern terms. They have absolutely nothing to do with this phenomenon. In fact, they're nothing but an obstacle. Now, I want to talk a little bit about some of the kinds of games that Wells plays. This is from his book about the politically incorrect guide to Darwinism. And this one really annoys me because I know Bill Ballard. Well, I did. He's died since. Bill Ballard was a fish embryologist, so he's in my field. He was a very well-regarded person in my field, a wonderful researcher, exciting to be with, a great speaker, and he discovered various things that are really important, and he's also the guy who named the Pharyngula. And what this is a quote from Jonathan Wells in his book. And he's saying, it's only by semantic tricks and subjective selection of evidence, by bending the facts of nature, that one can argue that early embryo stages of vertebrates are more alike than their adults. Now here's the funny thing. Nobody in biology claims that the earliest stages are more similar to each other. I showed you that developmental hourglass. It says exactly the opposite. It says they're very divergent at the early stages and they converge on a particular stage. So this is a strange complaint to make. So you might be wondering why Bill Ballard says this. Also notice that it's talking about semantic tricks and playing games with the evidence. Well, this is what Jonathan Wells does, because I looked the paper up that he took this quote from, and this is just a general rule. Whenever you see anything by a creationist with quote marks and ellipses, or that's chopped up, there's something important missing. So this is just one example. This is, oh, let's see, can we move this once again? You're very handy here. Thank you very much. Yeah. This is the actual quote. What he's saying is only by these semantic tricks can you claim that gastrolas, an earlier stage than the Pharyngula stage, are different. Wells has neatly snipped out this qualifier where he's talking about a very specific stage of development where he was an expert on gastrulation, for instance, where he knew that there was a great deal of variation. This is well before the Pharyngula stage when we have the convergence. So Wells has butchered a quote in order to make this point for himself. Okay, let's see how much we got here. This is another quote from that same paper by Ballard. So Wells is quoting Ballard and arguing, oh, well, Bill Ballard says they're very different. No, he didn't. When you read the actual paper, this is straight from Bill Ballard. He says that they're remarkably uniform through the particular stage, through the pharyngeal stage, and he talks about the standardized Pharyngula stage. This is a paper by Bill Ballard that says that there is a similarity of form at a Pharyngula stage in vertebrates. Jonathan Wells is quoting it and saying, Bill Ballard says there is no uniform stage in vertebrates. This is what I mean by liars. This is criminally bad scholarship that Wells is practicing. Okay, another point I want to make. One of the goals of the Discovery Institute and other creationist organizations is to make you more stupid. This is their agenda, simply put, is they don't want you to get the scientific information. So what they're going to do is they're going to corrupt education. They're going to destroy your textbooks until you can go to school and not learn a single damn thing and maybe believe what they say. Because you've got to be both ignorant and stupid to believe in intelligent design. Okay, what this is, in Wells' book, he has a little appendix where he's going to grade textbooks. And he's going to go through a great many American textbooks and evaluate them for whether they're good or not and give them grades. So, for instance, these are some of his criteria. If he's going to give a textbook a D if it uses photos rather than Haeckel's drawings. Think about this. You will get a D if you get a camera and take a picture of something that contradicts what Wells says. So he's damning books for that. And he's also got other things like if he talks about embryos as evidence for common ancestry. Evidence, yes, they are. Embryos are great evidence for common ancestry. Or if you use the colloquial term gill slits to describe pharyngeal pouches, which many textbooks do. It's not to say they're gills. Gill slits it's just a colloquial term for those little hang-me-down things in their throat. And then he gives them an automatic F if they use any of Haeckel's drawings. As I told you, Haeckel's drawings are not that bad. There was one that he cheated on. The other ones he kind of simplified, but often that's what you want to do in a textbook because you want a simplified version. So he's going to give D's or F's. There was no point in showing you the A, B, and C criteria because no textbook in the world meets his standards there, except I imagine the crap the Discovery Institute puts out. Okay, so just to give you some examples. This is from Campbell's Biology in the 5th edition. This was a book I actually taught from for about 5 years, different editions of this. And what he's got, what's in the textbook is this shows you the actual picture in the textbook. It shows you a photograph of a chick embryo, it shows you a photograph of a human embryo, and it's got nice little arrows. It says, okay, they both have gill pouches, they both have a postnatal tail, and it's got a little bit of text summarizing these similarities there. For the sin of showing photographs of human and chicken embryos, he gave it an F. This is pretty good, actually. This is a nice, simple summary. Then there was another book. I'll give you one more example. This is Gutman's Biology, the 1st edition, and it's got a little gray box on the page that is giving you a historical overview of this. It shows there's Haeckel's drawings, and I know it's tiny print, but if you read this print, what it says is that it says, okay, in the 19th century there was this theory called, ontogeny recapitulates phylogeny, etc., and that it's only partly true. It's useful for thinking about ontogeny and phylogeny, but it actually gives the historical rationale and explains why we don't follow this anymore. For actually accurately representing the history of an idea, you get an F. So this is the kind of thing we're getting from the creationists over and over again. Total lies and fraud, distortions. They have, okay, I'm sure Scotland is perfect, right? But in America, we have things like the textbook review process that goes on in Texas. That means publishers actually pay attention to idiots like Jonathan Wells and do their best to dilute the content of our textbooks. Okay, I'll just wrap this up because I've been babbling long enough. Let's look at the final lesson here. I just want to say a few points to leave you with. First of all, evidence is important. It's central to science. You cannot do science unless you are gathering evidence. Go out there and get data, do experiments, make observations. But at the same time, let's not neglect theory. Theory is important for guiding experiments. And one of the things that the history of this particular phenomenon has shown us is that theory colors what kind of experiments you do. And sometimes theories are predictive and useful. And I would say that the molecular story behind the phylogenetic pattern right now is very useful because it's telling us a lot about the genes that are involved in this process. Good theories are predictive and useful and diligent towards the evidence. That's the only thing that makes a theory useful, is if it allows us to do more experiments and more tests and leads us to deeper understanding. And you have to be very cautious and use the evidence appropriately. I would say that this is another point that severely damns the intelligent design movement because they don't bother with gathering evidence. And as I showed you, when you've got people like Jonathan Wells behind the wheel, they're pretty cavalier with what evidence they do use. I'd also add that intelligent design is not a useful theory. There is absolutely nothing we can learn from it. And bad theories do that. They disregard the evidence and they emphasize ideology. And I have to tell you that intelligent design fits this one particularly well. Intelligent design is very, very bad science. Okay, now I've loaded your heads with all kinds of stuff. I have one more point there. Oh yeah, creationists aren't just targeting biology. All of science and history are to be corrupted. They're screwing up your history books. So we got to watch out for them at every level. Okay, I think that's enough. Let me just leave you with one last thing. And this is going to be really hard to read. But just for reference, remember I told you that there are these 10+1 questions that the idiot creationists left for me. Every single one of them founded on a false premise. And just in case anybody wants to ask them of me, I'll leave them up here as a reference. But otherwise, if anybody wants to ask me intelligent questions, I would appreciate that too. Thank you.